Hello everyone, welcome to the third day of the way towards becoming a data scientist. And today we'll continue our last discussion about the probabilities, and we'll see today about the binomial distribution and the central limit theorem. So let's get started. Okay, so if you remember yesterday, we saw how can we get an overall a probability distribution chart or a table from by conducting an experiment. Now let's discuss how to evaluate the probabilities of outcomes in the game without actually conducting any experiment. Suppose your experimental setup involves how we saw it yesterday with three red balls and two blue balls, and we want to calculate the profitability of different combinations of red and blue balls being drawn. What if you want to explore other combinations, like two red and three blue balls, or four red and one blue ball, without physically carrying out the experiment? Is there any way to generalize these experiments? So today we'll see that how to generalize such problem using a commonly occurring and useful probability distribution called binomial distribution. Now, let's consider a scenario where you don't have the resources to conduct an experiment where people draw four balls from a bag. Can you still predict the probabilities? Absolutely. Now, let's start by calculating the probability of drawing two red balls in four trials. Now, since these balls are replaced after each draw, the probability remains the same for each draw. So we'll start by calculating the probability of drawing one red ball in a single trial. So the probability of drawing one red ball is 3 by 5 because we have 3 red balls and 5 total balls, which gives us 0.6. Now, if we want to calculate the probability of drawing no two red balls in four trials, we can use the multiplication rule of probability. The probability of drawing two red balls in the first two trial is, so the probability of two red balls is 0.6 multiplied by 0.6, which gives us 0.36. But what about drawing three red balls? To find the probability of getting three red balls, you should now need to consider all the possible sequences in which these balls could be drawn. So we have all the combinations here. It could be like three balls in the beginning and then one blue ball, or first is the blue ball and next three is the red ball, and so on. So for each sequence, the probability would be, so the probability for each sequence, so we have one blue and three red. It gives us, because we have two blue balls, overall 5 multiplied by 3.5 multiplied by 3.5 multiplied by 3.5, which gives us 0.0864. Let's say, so probability of drawing red ball is not equal to 0.6, but let's say any number as p. So the probability of drawing a red ball 4 times is given by p multiplied by p times p should be 4, p to the power 4. Similarly, the probability of drawing two red balls would be given by p into 1 minus p, because we have a blue ball in the mix and another blue ball, which gives p square one minus p whole square. But this combination is possible for 6 times. I mean, six kind of various combination is possible for two red balls and two blue balls. So in that case, we just multiply it with 6 and we get 6 into p square into 1 minus p square as the final. Similarly, for p equal to 3 red balls, we get p into p into p into 1 minus p. and this gives us p cube into 1 minus p, and since we saw that the four kind of combinations are possible, so it should give us 4p cube into 1 minus p. And if we get, let me just erase this, and if we want to find the probability of no red balls, then it should be 1 minus p into 1 minus p into 1 minus p into 1 minus p, and that gives us 1 minus p whole to the power 4. Okay, now generalizing it even more, instead of saying that there are like 0 red balls or 1 red balls, let's just generalize and let's say that in this experiment we need to take out r red balls out of total number of n balls. So in that case, for example, if we need to say p r equal to 2, that means that we have to multiply p into p r times and 1 minus p n minus r times. And the number of combinations possible is given by NCR. So the formula for finding the binomial probability is given by P of R instances as number of combination possible, PR to 1 minus P n to the power R. Just remember that n is the total number of trials. P is the probability of success. R is the number of success after n trials. And we have to follow some conditions that for this formula to apply. That is, the total number of trials is fixed. That is, we have fixed n number of trials. Each trial is binary, that only has two possible outcomes. So either a success, that is, so in this instance, it's a red ball or not. So either success or failure. And number 3 is the probability of success is same for all the trials and it's denoted by P. Now, from the above experiment, if we want to find out how many people actually lost the game, we can just do something called as cumulative probability, where we just add the number of probability to get a particular probability. That is, if we want to find how many people got less than 3 red balls, we can just add up to 0, 1, and 2 to find how many people actually got this. This is called a cumulative probability function. So if we try to put it in a table, it should look like this, and the overall cumulative probability should have the value of 1. And if we want to plot it, the plot should look something like this. So it should increase with each trial because we are actually adding it up, we are actually accumulating the value. So this is called a cumulative distribution function. Now, let's dive into probability density functions. Okay. Now, for a continuous random variable, the probability of getting an exact value is very low. Actually, it's almost 0. So, when we are talking about the probability of continuous random variable, we can talk only in terms of intervals. For example, let's say for a particular school, the probability of the students commuting between exactly like 30 minutes should be 0. But the probability of the student having the commute time between 28 to 32 minutes is 0.2. Hence, the continuous random variable and probability density functions and cumulative distribution functions are used instead of the bar chart type of the distribution used for the probability of discrete random variables. These functions are preferred because they talk about the probability in terms of intervals. To find the cumulative probability using a CDF, you just have to check the value of the graph. For example, here, if you want to find which students take exactly like 28 minutes to reach the school, the probability is given by the value of the CDF at x equal to 28, and in the PDF it is given by the area under the curve, which is between 20 to 28. Now, now we know why the PDF are the best choice, because it helps to give the value between an interval or between the continuous variables. And so one of the most commonly used probability density function is the normal distribution function. The normal distribution is a symmetric distribution. That means that its mean, median, and mode lie at the center. Also, a variable that is normally distributed follows the 1, 2, 3 rule, which states that 68% probability of the variable lying within one standard deviation. So 68% of the variable lies within one standard deviation, 95% probability of the variable lying within two standard deviation, and 97% of the variable, the probability of lying 97%, the 99.7% probability of the variable lying within three standard deviation of the mean. Now, in order to find the probability of a normal variable, you do not actually need to know the value of the mean or the standard deviation. It is enough to know the number of standard deviations away from the mean your random variable is, and that is given by something called a z-score, which is given by, z is equal to x minus the mean by standard deviation. This is called the z-score or the standard normal variable. In fact, you can use the z table to find the cumulative probability for various z. For example, you want to find the cumulative probability of z equal to 0.68 using the z table. You have to find the intersection of the row 0.6 and the column of 0.08, which will give a particular value, and that's how you can get the cumulative probability for z equal to 0.68. So I hope you understood about the binomial distribution and the probability density functions. And we'll continue this discussion tomorrow about the sampling methods, the population, and also the central limit theorem. Thank you. See you tomorrow. Bye-bye.